Nenomatica, where mathematics meets YouTube excellence. Welcome to our math lesson. Today, we're going to solve a challenging inequality proof. Let's start by understanding the problem. Example, if we have a plus b equals 1, where a and b are both positive numbers, prove that the quantity a plus 1 over a squared plus the quantity b plus 1 over b squared is greater than or equal to 25 over 2. Let's start our proof. We'll make a substitution to simplify the problem. Let x equal a plus 1 over a, and y equal b plus 1 over b. So our inequality becomes x squared plus y squared is greater than or equal to 25 over 2. This substitution helps us transform our complex expressions into simpler variables, making the inequality easier to manipulate. Step 2. Let's apply the Cauchy-Schwarz inequality. This inequality tells us that for any two sets of numbers, the square of the dot product is less than or equal to the product of the sum of squares. In our case, we can represent it as x squared plus y squared over 2 is greater than or equal to the quantity x plus y over 2 squared. Step 3. Let's simplify the right side of our inequality. We have a plus 1 over a plus b plus 1 over b all over 2 squared. Since we know that a plus b equals 1, we need to determine what 1 over a plus 1 over b equals. Step 4. Now we'll use the arithmetic mean harmonic mean inequality to handle the term 1 over a plus 1 over b. This inequality states that the arithmetic mean is greater than or equal to the harmonic mean. Specifically, 1 over a plus 1 over b over 2 is greater than or equal to 2 over a plus b. Since a plus b equals 1, we get 1 over a plus 1 over b is greater than or equal to 2. It's important to note that this inequality holds because a and b are positive numbers as specified in our original conditions. Step 5. Let's continue with our proof. Using the fact that 1 over a plus 1 over b is greater than or equal to 4, we can write 1 plus 1 over a plus 1 over b is greater than or equal to 5. Squaring both sides, we get the square of 1 plus 1 over a plus 1 over b is greater than or equal to 25. Step 6. Now we can complete our proof. We have shown that the square of 1 plus 1 over a plus 1 over b is greater than or equal to 25. Substituting this back into our earlier inequality, we get 1/2 times the sum of a plus 1 over a squared plus b plus 1 over b squared is greater than or equal to 1/4 times 25. Simplifying, we get a plus 1 over a squared plus b plus 1 over b squared is greater than or equal to 25 over 2, which is exactly what we wanted to prove. Let's look at our example. We need to minimize the expression s equals 1 over x plus 1 over y plus 1 over z, given that x plus y plus z equals k, where k is greater than 0, and x, y, and z are all positive. We'll solve this using the Cauchy-Schwarz inequality. Let's recall what this inequality states. For positive numbers, a1, a2, and so on up to an, and their reciprocals, the Cauchy-Schwarz inequality tells us that the product of the sum of the a's and the sum of 1 over a's is greater than or equal to n squared. Now, for our three variables x, y, and z, we can apply this inequality directly. According to the Cauchy-Schwarz inequality, for these three positive variables, we know that the product of x plus y plus z and 1 over x plus 1 over y plus 1 over z is greater than or equal to 3 squared, which is 9. Let's substitute what we know into this inequality. We know that x plus y plus z equals k from our constraints, and s is defined as 1 over x plus 1 over y plus 1 over z. So we can rewrite our inequality as k times s is greater than or equal to 9. Now we can solve for s. Dividing both sides by k, we get s is greater than or equal to 9 over k. Therefore, the minimum value of s equals 9 over k. This occurs when x, y, and z are all equal, which is when equality holds in the Cauchy-Schwarz inequality. Let's look at our problem. We need to find the minimum value of y equals x squared minus 3 divided by the square root of x squared minus 4, where the absolute value of x is greater than 2. Let's start with our given function. We have y equals x squared minus 3 divided by the square root of x squared minus 4. To simplify this function, let's try to manipulate the numerator. We can rewrite the numerator as x squared minus 4 plus 1, which gives us y equals x squared minus 4 plus 1, all divided by the square root of x squared minus 4. Now, let's split this into two separate fractions. We get y equals x squared minus 4 divided by the square root of x squared minus 4, plus 1 divided by the square root of x squared minus 4. Let's focus on the first term. We can multiply both the numerator and denominator by the square root of x squared minus 4. In the numerator, we get x squared minus 4 times the square root of x squared minus 4 divided by x squared minus 4, which equals the square root of x squared minus 4. So our function becomes y equals the square root of x squared minus 4 plus 1 divided by the square root of x squared minus 4. Now, we need to find the minimum value of this expression. We know that for any two positive numbers a and b, their sum is minimized when they are equal. Here, we have a equals the square root of x squared minus 4, and b equals 1 divided by the square root of x squared minus 4. By the AMGM inequality, we know that the sum of two numbers is always greater than or equal to twice the square root of their product. In our case, the product is the square root of x squared minus 4 times 1 divided by the square root of x squared minus 4, which equals 1. Therefore, the minimum value of the sum is 2 times the square root of 1, which is 2. This means y is greater than or equal to 2. For the minimum to occur, both terms must be equal. That happens when the square root of x squared minus 4 equals 1 divided by the square root of x squared minus 4. Let's solve this equation. Squaring both sides, we get x squared minus 4 equals 1 divided by x squared minus 4, which gives us x squared minus 4 squared equals 1. Since the absolute value of x is greater than 2, we know that x squared is greater than 4, so x squared minus 4 is positive. Therefore, our minimum value is 2, which occurs when x equals plus or minus the square root of 5. Therefore, the minimum value of our function is 2. Let's start with our example. We need to find the minimum value of the expression y equals 4x squared minus 8 divided by the square root of x squared minus 3, where the absolute value of x is greater than square root of 3. Let's start by simplifying the numerator. We can rewrite 4x squared minus 8 as 4 times x squared minus 2. Next, we can factor out the 4 from the numerator, which gives us y equals 4 times the fraction x squared minus 2 over the square root of x squared minus 3. Now, let's manipulate the numerator. We can rewrite x squared minus 2 as x squared minus 3 plus 1. Our next step is crucial. We can split this fraction into the sum of two fractions x squared minus 3 over square root of x squared minus 3 plus 1 over square root of x squared minus 3. Now we can simplify the first fraction. Notice that x squared minus 3 over square root of x squared minus 3 can be rewritten as the square root of x squared minus 3, since the square root of x squared minus 3 times itself equals x squared minus 3. Let's simplify this further by bringing together the terms with square roots. We now have y equals 4 times the sum of square root of x squared minus 3 plus 1 over square root of x squared minus 3. We now need to find the minimum value of this expression. Let's first recall a property of the sum of a number and its reciprocal. For any positive number, a, the sum of a plus 1 over a is always greater than or equal to 2. The minimum value of 2 is achieved when it equals 1. To find when the minimum occurs, we need to determine when square root of x squared minus 3 equals 1. This happens when x squared minus 3 equals 1 squared, which simplifies to x squared equals 4, and therefore x equals plus or minus 2. Now, when x equals plus or minus 2, the sum of square root of x squared minus 3 plus 1 over square root of x squared minus 3 equals 2. Therefore, y equals 4 times 2, which equals 8. Finally, we can conclude that the minimum value of our function y equals 4x squared minus 8 divided by the square root of x squared minus 3, where the absolute value of x is greater than square root of 3, is equal to 8. Let's begin with our example. We need to find the maximum and minimum values of the function y equals x divided by x squared plus 1. Let's start by taking the reciprocal of both sides of the equation. This gives us 1 over y equals x squared plus 1 over x. Let's simplify the right side further. We get 1 over y equals x plus 1 over x. Now, we'll analyze two cases. First, let's consider when x is greater than 0. If x is positive, we can proceed with our analysis. We know that for any positive number x, the sum x plus 1 over x is always greater than or equal to 2. This is a well-known inequality that can be proven using calculus or the AMGM inequality. Now, if 1 over y is greater than or equal to 2, then y must be less than or equal to 1/2. Now, let's examine the second case, when x is less than 0. When x is negative, we need to be careful with our inequality. For any negative x, the sum x plus 1 over x is always less than or equal to -2. This means that 1 over y is less than or equal to -2 when we take the reciprocal of both sides. And noting the change in inequality direction, we get y is greater than or equal to -1/2. Now, let's combine our results from both cases. From the first case, we found that y is less than or equal to 1/2 when x is positive. From the second case, we found that y is greater than or equal to -1/2 when x is negative. Therefore, we can conclude that the range of our function is from -1/2 to +1/2. So, the maximum value of our function is 1/2, and the minimum value is -1/2. Let's start with our example. We have the expression a equals a squared plus b squared plus c squared, multiplied by the quantity 1 over a squared plus 1 over b squared plus 1 over c squared. Our task is to find the minimum value of a. To solve this problem, we'll use the Cauchy-Schwarz inequality. This is a powerful tool in mathematics that helps us find minimum or maximum values. Now, let's recall the Cauchy-Schwarz inequality for 3 variables. As we can see here, for any positive real numbers, a, b, and c, the sum of plus b plus c, multiplied by 1 over a plus 1 over b plus 1 over c, is always greater than or equal to 9. In our problem, we need to apply a substitution. Let's substitute a 1 with a squared, a 2 with b squared, and a 3 with c squared. This gives us the inequality that a squared plus b squared plus c squared, multiplied by 1 over a squared plus 1 over b squared plus 1 over c squared, is greater than or equal to 9. Looking at this inequality, we can recognize that the left-hand side is exactly our expression a. Therefore, a is greater than or equal to 9. Now that we know a is always greater than or equal to 9, we need to determine if a can actually equal 9, which would be the minimum value. In the Cauchy-Schwarz inequality, equality occurs when the variables are proportional. In our case, this means a squared, b squared, and c squared must be equal. Therefore, the minimum value of a equals 9, which occurs when a b and c are equal. Let's look at our example. We want to find the maximum value of y equals x squared divided by 1 plus x to the 4th power, where x is not equal to 0. Let's begin solving this problem. First, we'll rewrite our equation. The original expression y equals x squared divided by 1 plus x to the 4th power can also be written as y equals 1 divided by 1 plus x to the 4th power, all multiplied by x squared. Next, we'll rewrite this as y equals 1 divided by the fraction 1 plus x to the 4th power divided by x squared. This will help us manipulate the expression further. Now, we notice that 1 divided by x squared times x squared equals 1, which is greater than 0 for any non-zero value of x. Next, we can apply the arithmetic mean geometric mean inequality, or AMGM inequality. This tells us that for any positive real numbers, the sum of 1 over x squared plus x squared is greater than or equal to 2, with equality when 1 over x squared equals x squared. From the previous step, we know that 1 over x squared plus x squared is greater than or equal to 2. Using the property that if a fraction's denominator increases, the fraction's value decreases, we can say that 1 divided by the quantity 1 over x squared plus x squared is less than or equal to 1/2. Since we've established that 1 divided by the quantity 1 over x squared plus x squared is less than or equal to 1/2, and this expression is equal to y, we can state that y is less than or equal to 1/2. Therefore, the maximum value of the expression y equals x squared divided by 1 plus x to the 4th power is 1/2. We can verify this result by finding when the maximum occurs. The maximum occurs when equality holds in the AMGM inequality, which happens when 1 over x squared equals x squared. Solving this equation, we get x to the 4th power equals 1, or x equals plus or minus 1. When we substitute either of these values back into our original expression, we indeed get y equals 1/2, confirming our answer. Let's start with our example. We have the system of equations. X, y, z times the quantity x plus y plus z equals 1, and we're told that x, y, and z are all positive values. Our task is to find the minimum value of the expression the quantity x plus y times the quantity y plus c. Let's begin by expanding the expression to understand what we're trying to minimize. Using the distributive property, we can expand the quantity x plus y times the quantity y plus c as follows. We get xy plus xz plus y squared plus yz. This can be rearranged as y times the quantity x plus y plus c plus xc. Now, we can use our constraint to simplify the expression further. From our constraint, we know that xyz times the quantity x plus y plus c equals 1. If we solve for the quantity x plus y plus c, we get x plus y plus z equals 1 divided by xyz. Now we can substitute this expression for x plus y plus c into our rearranged expression. From steps 1 and 2, we know that our original expression equals y times the quantity x plus y plus z plus xc. Substituting x plus y plus z equals 1 divided by xyz, we get y times 1 divided by xyz plus xc, which simplifies to y divided by xyz plus xc. This further simplifies to 1 divided by xz plus xc. Now we can apply the AMGM inequality to find the minimum value of our expression. For any positive real numbers a and b, their arithmetic mean is always greater than or equal to their geometric mean. That is, a plus b divided by 2 is greater than or equal to the square root of a times b, with equality when it equals b, in our case, with a being 1 divided by xc, and b being xc. We have the quantity 1 divided by xc plus xc divided by 2 is greater than or equal to the square root of 1 divided by xc times xc, which equals 1. Therefore, 1 divided by xz divided by 2 is greater than or equal to the square root of 1 divided by xc times xc, which equals 1. Therefore, 1 divided by xz plus xc is greater than or equal to 2. The minimum value of 2 is achieved when 1 divided by xz equals xc, which means xz equals 1. Now we can finalize our solution. Our original expression, the quantity x plus y times the quantity y plus c, is equal to 1 divided by xz plus xc. We've shown that 1 divided by xz plus xc has a minimum value of 2 when xz equals 1. Therefore, the minimum value of the original expression, the quantity x plus y times the quantity y plus z, is 2. We are given that AC plus BD equals PQ, where all variables A, B, C, D, P, and Q are positive numbers. We need to prove that the product of the sum of squares, specifically a squared plus b squared multiplied by c squared plus d squared, is greater than or equal to p squared, q squared. To solve this problem, we'll use a powerful mathematical tool called the Cauchy-Schwarz inequality. This inequality states that for any vectors a1, a2, and b1, b2, the following relation holds: the sum of squares of a1 and a2 multiplied by the sum of squares of b1 and b2 is greater than or equal to the square of a1 b1 plus a2 b2. Now, let's apply this inequality to our problem. We can identify a1 as a, a2 as b, b1 as c, and b2 as d. By substituting these into the Cauchy-Schwarz inequality, we get the sum of squares a squared plus b squared multiplied by the sum of squares c squared plus d squared is greater than or equal to the square of ac plus bd. Now, we can use our given equation. We know that ac plus bd equals pq, so we can substitute this into our inequality. This gives us a squared plus b squared multiplied by c squared plus d squared is greater than or equal to pq squared. Simplifying further, we have a squared plus b squared multiplied by c squared plus d squared is greater than or equal to p squared, q squared, which is exactly what we wanted to prove. Let's now look at another example. In this problem, we have a sequence defined by u sub n equals 1 plus 1 over n to the power of n, where n is a positive integer. We need to prove that u sub n plus 1 is greater than u sub n. For this problem, we'll use a mathematical inequality that states, for positive a and lambda greater than 1, 1 plus alpha to the power of lambda is greater than 1 plus alpha times lambda. Let's define alpha as 1 over n plus 1 and lambda as n plus 1 over n. With these substitutions, let's see what we can derive. Now, applying the inequality with our values of alpha and lambda, we get 1 plus 1 over n plus 1 to the power of n plus 1 over n is greater than 1 plus 1 over n plus 1 times n plus 1 over n. Simplifying the right side, we get 1 plus 1 over n, which is equivalent to n plus 1 over n. Let's now raise both sides to the power of n. This gives us 1 plus 1 over n plus 1 to the power of n plus 1 is greater than n plus 1 over n to the power of n. We know that n plus 1 over n to the power of n equals 1 plus 1 over n to the power of n. So we have 1 plus 1 over n plus 1 to the power of n plus 1 is greater than 1 plus 1 over n to the power of n. This is exactly what we wanted to prove. U sub n plus 1 is greater than U sub n. Let's summarize what we've learned today. We proved two important inequalities. First, we showed that the product of the sum of squares is greater than or equal to the square of the sum of products, which is a specific application of the Cauchy-Schwarz inequality. Second, we proved that the sequence defined by U sub n equals 1 plus 1 over n to the power of n is strictly increasing. Both proofs relied on fundamental inequalities in mathematics, demonstrating how these powerful tools can be used to solve complex problems. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. Nenomatica, where mathematics meets YouTube excellence.